All right, welcome to section 14.3, where we're now getting into taking derivatives of a two independent variable function. And so we're going to start off with using partial derivatives. So considering the heat index function I, which is the perceived air temperature when the actual temperature of cap T is the relative humidity, and the relative humidity is cap H. So I is a function of T and H, and we can define, and we can write I equal to f of cap T, cap H, which we've dealt before, and we've called this table kind of like the humidex. The highlighted column corresponds to a relative humidity of cap H is equal to 70%. The heat index is a function of the single variable cap T for a fixed value of H. So let's write G of T is equal to F of T of 70. The derivative of G when T is equal to 96 degrees Fahrenheit is the rate of change of I with respect to T when the temperature is 96 degrees Fahrenheit. So we'll go ahead and find G prime of 96 using limits, and we're going to go first with a step of positive 2 for the humidity, and then a relative humidity, and then minus 2 to find G prime of 96. And so we have the limit as H approaches 0, plug in positive 2, we're going to get 133 minus 125 over 2, which is just 8 over 2, which is equal to 4. If we find the value 1 less than on our table of 96, we have H is negative 2. So we get 96 minus 2 minus G of 96. So 118 minus 125, which is negative 7. Divide that by negative 2, we get 3.5. So averaging these two values, we can say that derivative G prime of 96 is approximately 3.75. This means that when the actual temperature is 96 degrees Fahrenheit and the relative humidity is 70%, the apparent temperature heat index rises about 3.5 degrees for every degree that the actual temperature rises. Now, let's look at the highlighted row, which corresponds to the fixed temperature T is equal to 96 degrees Fahrenheit. The numbers in this row are values of the function G of cap H, which is the function 96 cap H, which describes how the heat index increases as the relative humidity at H increases when the actual temperature is 96 degrees Fahrenheit. The derivative of this function when H is equal to 70% is the rate of change of I with respect to H when H is equal to 70% Fahrenheit. So now, instead of going instead of going vertically, now we're going to go horizontally and find how the temperature is changing when the humidity stays the same, but the actual temperature changes. So we can approximate G prime of 70 by taking H is equal to 5 and negative 5, corresponding the 5 to our steps for our temperature. And so when we have G prime of 70, the limit H of 0, the limit as H approaches 0, G is 70 plus 5, which is 75, minus G of 70 divided by 5. So 130 minus 125 over 5 is just 1. G prime of 70, the limit as H approaches 0, is going to be G of 65 minus G of 70 over negative 5, which is just 121 minus 125 over negative 5, which is 0.8. By averaging these values, we get the estimate G prime of 70 is about 0.9. This says that when the temperature is 96 degrees Fahrenheit and the relative humidity is 70%, the heat index rises about 0.9 degrees Fahrenheit for every percent that the relative humidity rises. In general, if f is a function of two variables, x and y, suppose we let only x vary while keeping y fixed. Say y is equal to b, where b is a constant. Then we are really considering a function of a single variable x, namely g of x, which is equal to f of x, b. If g has a derivative at a, then we call it the partial derivative of f with respect to x at a, b, and denote it by f sub x ab. Thus, f of sub x ab is equal to g prime of a, where g of x is equal to f of xb. by definition of derivative, we have g prime of a is equal to the limit as g of a plus h minus g of a over h. So we have f sub x ab is equal to the limit as h approaches 0, f of a plus hb minus f of ab over h. And the same thing can be said with the y's. Again, you can go ahead and read the rest of this. So basically what we're doing is we're finding, because we're taking the derivative of a function with two independent variables, there are an infinite number of derivatives that we can take at a single point, just because of the way that we have a curve in three-dimensional space. So what we're doing now is we're taking direction derivatives, but only from two directions. All right, we'll actually do more direction derivatives later, but what we're doing is, at a specific point, I'll just draw a picture of it real fast. At a specific point, say, here's our three-dimensional plane, all right, where that's x, that's y, and that's z. Again, this is not perfect. Right, if we have some point, we have a curve, right, and say at that point, what we're doing is we're taking the derivative in the x direction, so that would be our partial derivative of x, and then also at that point, we're taking it of y. So that would be f of y. And so that's what we're doing. We're just taking derivatives in two directions. A direction on the x-axis and a direction on the y-axis. And that's what, the partial derivatives that we're doing for today. Again, we can do direction derivatives, which is, we can say a direction and we can take the derivative, that way.